Hello everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In today's class we will continue our discussion of the hard margin support vector classifier and delve into the mathematics behind it. So let us go ahead and get started. So the topic for today is mathematical formulation of hard margin support vector classification, so SVC. And if you recall the illustration that was shown last time, and this was shown in a 2-dimensional feature space, that there were two sets of classes that you want to distinguish, right, and I am drawing these right in the space of two features, but really you can draw it in the space of any number of features, and the goal was to find this hyperplane which maximizes the distance between itself and the support vectors, right. So this is one of the support vectors and then this is the other support vector. So these are called support vectors and this is the hyperplane. Okay. So how do we go ahead and formulate this mathematically? Okay. So what we need to do is we want to maximize, right, the margin which is essentially this distance, also denoted as d closest, which is the distance between the hyperplane chosen and the support vector and one of the support vectors. Okay. So if you look at this, the distance, right, between of a point to a plane can be written as follows. So this d is the distance of a point x naught to the hyperplane, right, and by distance we are referring to the orthogonal perpendicular distance. Okay. So this distance can be written and this can be of course shown for a line but also for a hyperplane. So this is simply beta transpose x naught plus beta naught divided by the norm of beta. This is a standard result when you do geometry. You would have in your high school found the distance between a point and a line, right. This is simply the extension of the same concept to find the distance between a point and a hyperplane, right, because we are operating in p-dimensional feature space, right. Now you will see how this problem gets simplified, right. If you remember what we had done for the decision boundary. So to make the decision you had said that yi times beta transpose xi plus beta naught will always be greater than or equal to 1. This is what you had said, right, for the 2 points, and this we wrote in the previous class. Now for the support vector, what will happen, right. Let us take yi equals 1, right. So we are taking the point, this particular point on the support vector. So yi equals 1 and thus beta transpose xi plus beta naught greater than equal to 1. This is true for points that are away from the support vector, right, but exactly on the support vector it will be equal to 1. So thus beta transpose xi plus beta naught greater than equal to 1 for points away from the support vector. But for points on the support vector, your beta transpose xi plus beta naught will be exactly equal to 1, right. And again this is something which you have studied in high school. Whenever you sketch inequalities based on lines, you know that on the line segment an equality holds and away from the line the equality becomes an inequality. So the same concept can be extended to a hyperplane. So for points exactly on the support vector, beta transpose xi plus beta naught equal to 1, and that is exactly what we have here, right. Beta transpose x naught plus beta naught. We want to find the distance of a point that is on the support vector to the hyperplane, right. This is the distance we want to find, the d closest, and the equation of the hyperplane is beta transpose x plus beta naught equal to 0. So then we will just plug in a point on the support vector x naught, and we know that for points exactly on the support vector, let me call it x naught, beta transpose x naught plus beta naught equal to 1, and now you can plug this into the equation above. Okay. So when you plug this here, you can clearly see that d closest is equal to 1 divided by the norm of beta. Okay. So this is what happens in this hard margin support vector classification. Okay. So we want to maximize this margin, but for computational convenience it is formulated slightly differently as a minimization problem, right. Most problems in optimization theory are written as minimization problems. So instead of maximizing 1 over norm beta, what we end up doing is we minimize half of the norm of beta squared. Okay. And this is done in support vector classification. So the problem that the optimization problem that we wish to solve is we want to minimize half normed of beta squared, which is essentially equivalent to maximizing the margin, the distance between the decision hyperplane and the support vectors, and this of course is being done to find the optimal parameters, the weights beta and the bias beta naught, such that the classification condition which we had written a little while ago, yi times beta transpose xi plus beta naught should be greater than equal to 1, right. This we had written here and as well as in the previous class. This is the condition which needs to be satisfied by the points, right. That is how you will know that some of the points are in this region and some of the points are in this region. Okay. So this is the optimization problem that needs to be solved to develop a support vector classifier. Okay. I hope this makes sense to you. So essentially what we are doing is we have formulated a quadratic optimization problem with linear constraints. What are the constraints? The constraints are basically the inequalities which are enforcing that the points lie in the appropriate classes. Okay. So these are the constraints enforcing the points to lie in the correct regions of the feature space as divided by the optimal hyperplane. Okay. So, I hope you are able to appreciate how mathematically we are formulating the hard margin classification problem in support vector machines. Okay. So, once these optimal parameters beta and beta naught are obtained, any new point can then be classified very easily. So, let us see how that is done. So, once the optimal beta and beta naught, right, the weights and the biases of the model are obtained, any new point can be classified as yi hat is basically equal to plus 1 if your beta transpose xi plus beta naught is greater than equal to 0, and it is minus 1 if beta transpose xi plus beta naught is less than or equal to 0. Okay. So, in short, you could even write it using the sign function SGN which we have encountered previously. So, this is basically the sign of beta transpose xi plus beta naught, right, where SGN of x or the sign function not SINE is plus 1 if x is greater than equal to 0 and is minus 1 if x is less than 0. So, it tells you the sign of x. Okay, so, this is a slight modification of the sign function. Usually the sign function the output is 0 if x equal to 0, but for our problem we always wish to predict either plus 1 or minus 1. 0 is not an acceptable output, and therefore we have modified this sign function slightly. Okay. So, this is all that is in terms of the mathematical formulation of the hard margin classifier. Now, there is a challenge here, sometimes the data is not perfectly separable, then what do you do in that scenario, right? You have to still somehow create the classification boundary. So, let us go ahead and see what you will do in those scenarios. So, sometimes the data is not perfectly separable. So, it is not perfectly separable by the hyperplane, and in this case we employ what is known in optimization theory as slack variables. To account for errors. Right. Quite literally in English, when you say you have cut someone some slack, you have given them some allowance, right. So, in that spirit we are writing slack variables, right. So, you have given some allowance to the model to make some errors while it is making predictions. So, that is literally the meaning of these slack variables, they allow you to account for errors, and this approach is called soft margin classification. So, what we did previously was hard margin classification, and what we are going to do now, which involves the use of slack variables, is soft margin classification. Okay. So, let us see how this particular problem is mathematically formulated. It is very similar, you just allow for this error to be made, and we are going to write how this is done. So, this is soft margin support vector classifier, and here you are finding not only the weights and the biases, but also these slack variables, right, which allow you to make errors. So, you are minimizing half the norm of beta squared, sorry, half the squared norm of beta plus C, which is a regularization parameter which has been encountered previously by you, times the sum of these slack variables, right. So, this C is a regularization parameter, that is the penalty you are imposing to make these errors, right. If your regularization parameter is higher, you do not allow these errors to be made, and if this regularization parameter is 0, that means you return to the hard margin classification problem. Okay. So, this is the optimization problem subject to again the constraint that yi times beta transpose xi plus beta naught, that should be greater than equal to 1. I mean, it would have been greater than equal to 1 in hard margin classification, but now you have to account for some errors. So, that is using these slack variables. So, instead of greater than equal to 1, it becomes 1 minus xi I, where xi I is greater than equal to 0, and these are the so called slack variables which I had referred to here, and essentially they allow you to some allowance to make errors. Okay. So, what is going to happen now? So, if you have a higher regularization parameter, that means you have lower errors, you are penalizing the errors more. So, you are forced to have lower errors, but along with the lower errors you will also have a lower margin, right, because if you are making too much allowance here, you have to reduce half beta norm squared, and that means that your margin will be lower. And on the other hand, if you have lower C, then you have a higher errors. So, you pay more in terms of errors, but you gain by obtaining a higher margin. Okay. So, there is some trade off here. Of course, like with any regularization parameter, you have to do some kind of a cross validation. This is a hyperparameter, and can be fixed by some kind of a cross validation strategy. Okay. And this is something that you can look into when you are implementing these kind of models for a core engineering application. Okay. So, essentially if you want to write this down more conceptually, the introduction of the slack variables allows you a trade off between the separation of the hyperplane and the support vectors, and the error made by the classifier. right. So, this is exactly what you saw right above here. Okay. So, a higher C makes the model more generalizable typically, right, because you have a lower margin. So, that means you are not insisting too much on hard margin, and that means that it is not so rigid, the model is not so rigid. So, it is not overfit, and therefore, the model is more generalizable and robust to use. Of course, only a cross validation strategy will tell you how high of a C you should take. Should C be 1, should it be 0.1, because that will also depend on the values that the target variable can take, but you see how it can be adjusted. Okay. So, in terms of numerical implementation, it is often easier to solve a dual optimization problem. So, in optimization theory there is something known as the concept of duality. Any problem, right, you can write in terms of the dual problem, and that is what we will be doing here as well. So, in terms of the numerical implementation of the hard margin SVM classifier, we actually solve the dual optimization problem. So, in terms of the numerical implementation of the hard margin classifier, we solve the dual optimization problem corresponding to the primal problem which we had stated. So, the primal problem was basically what I had stated above, right, and we are now going to write the dual problem. Okay. So, this was the primal problem. And what we are going to do is we are going to write the dual to this, which is actually what is done numerically. Okay. So, let us see how this is done. So, to do this we have to write the Lagrangian of the problem, and remember we had talked about the Lagrangian some time ago when we were doing optimization with constraints in the context of a decision tree, where we had to ensure the constraint that the probability is sum to 1. So, that is what we are going to do now, we are going to write the Lagrangian of the problem. So, we first write the Lagrangian of the problem. Okay. So, let us see how that is done. So, the Lagrangian L is essentially half norm squared of beta minus the constraints, right, and the constraints you know were some I going from 1 to n yi times beta transpose xi plus beta naught minus 1, right. So, these are the constraints that have to be followed, and these are actually inequality constraints, right. These are not regular equality constraints which is used in the method of Lagrange multipliers, but these are actually inequality constraints, and these alpha I, these are the Lagrange multipliers. Okay. So, now what happens is we use an approach known as the Karush-Kuhn-Tucker approach. So, this is very well known in optimization theory. And essentially it lets you solve a much simpler problem. Generalizing the Lagrange multipliers to inequality constraint. Right. So, you take the method of Lagrange multipliers which works well for equality constraints and generalizes it to inequality constraints. What is the inequality constraint we are talking about? If you remember, the actual constraint is yi times beta transpose xi plus beta naught should be greater than equal to 1. So, this is an inequality constraint and that is introduced through this KKT approach. Okay. So, what we do here is that we solve the dual problem, okay. So, which is max of alpha where I going from 1 to n alpha I minus half of some I j going from 1 to n alpha I alpha j y I y j x I transpose x j, okay, such that sum I going from 1 to n alpha I y I equals 0 and alpha I is greater than or equal to 0. Okay. So, essentially what is happening here is that we are solving this dual problem and the motivation for introducing it, as we will see slightly later, is that it allows you to use the inner product between points, right, and the inner product is a very convenient way to introduce kernel functions, right. So, this is the dot product or the inner product between 2 points and is later used to introduce kernels within support vector machines. So, this is the inner product and then it can be used later to introduce kernel functions that bring in non-linearity. Okay. So, what happens now, right? So, alpha I plays a very important role here. So, alpha I greater than 0, it corresponds to the support vectors, and alpha I equal to 0 corresponds to basically other points not on the support vector. Right, these are the points that are easily classified. Okay. So, once these alpha I are obtained, right, you can now classify the point very easily. Any new point that you have can be classified very easily. Earlier you were looking at the sign of beta beta transpose x plus beta naught. If you remember, you are looking at the sign of beta transpose xi plus beta naught. Now, you can just talk in terms of a linear combination of the alpha i's. Okay. So, once the alpha I are obtained, you can obtain beta and beta naught, right. So, beta can be obtained as sum I going from 1 to n alpha I yi xi, and beta naught can be obtained from any support vector. Right, and once of course the alpha i's are obtained, you can just make the prediction as earlier using the sign function of beta transpose xi plus beta naught, and this can be written as the sign of sum I going from 1 to n alpha j yj xj transpose xi, sorry, j going from 1 to n alpha j yj xj transpose xi plus beta naught, right. So, I have just substituted the expression for beta into here. So, this is what I meant when I said you can obtain the prediction of the points using a linear combination, right, over all the points. So, this is where you are doing the linear combination that is done to obtain the weights beta, and then the bias of course was obtained from any support vector. Okay. So, this completes the dual problem formulation of the support vector machine. It is a bit mathematical, but I hope that this lets you understand how the support vector classifier is really implemented on a computer. And just for the sake of completeness, in soft margin classification, the dual problem constraint changes to 0 less than equal to alpha I less than equal to c, where again c is the regularization parameter, which tells you the constraint between how much you allow slack, right, in the prediction, and how much you are actually maximizing the margin. Okay. So, if you see the constraint that I had written here, right, in the hard margin classification alpha I was greater than equal to 0, in the soft margin classification alpha I is still greater than equal to 0, but it is less than regularization parameter c. Okay. So, this brings me to the end of this particular lecture. In this lecture we formulated the mathematics behind the hard margin classification and the soft margin classification. In particular, when you move from hard margin classification to soft margin classification, you introduce the concept of a slack variable, and then this slack variable tells you how much regularized the problem is and how generalizable your ML model is. We also talked about the dual formulation of the minimization problem through the use of the Karish-Kuhn-Tucker conditions. At this point the formulation is a bit mathematical, so I just told you the salient points. We did not go into any detailed derivations, but it suffices to say at the end of the day that you do solve the dual problem in optimization theory when you work with support vector machines, and then through the use of the dual problem there are certain advantages. First is that you are able to write the prediction as a linear combination of the inner products over all the points, and the second thing is the same inner product can be used later to introduce kernel functions that bring in non-linearity into the problem. Okay. So, I hope you learned something new today about support vector machines. Thank you for joining, and I will see you next time.